All right, today we're going to do something a little different. We're not just going to look at a piece of generative art, we're going to take it apart, line by line. We're diving deep into this one specific 3D audiovisual world to find the exact code that makes it tick, that weaves sight and sound together so perfectly. Okay, let's get into it.
First off, just experience it for a second. You've got this single box just floating in space. As it drifts up, the tone it's making rises with it. As it sinks, the pitch gets deeper. And that sound, it isn't just left and right. It has this real presence, right? It feels like it's actually moving past you. It's such a simple, mesmerizing loop, but the way it's built is just incredibly elegant.
And it really brings us to the big question here. How does this actually work? Not in some abstract way, but what are the specific commands that create this illusion? Well, it all boils down to two key pieces of technology working together in perfect harmony. So for everything you see, the artist is using P5JS. You can just think of this as the toolkit that gives us a super simple command to draw a box and a canvas to draw it on. It handles all the heavy lifting of getting graphics to show up in the browser. And then for everything you hear, there's the Web Audio API. Now, this isn't some library you have to download. It's a set of tools that's built right into your web browser. It's what lets us create a pure tone completely from scratch and, this is the crucial part, tell the browser exactly where in 3D space that sound should be coming from. Okay, let's kick things off with what we can see. We're going to trace the exact code that puts that box on the screen and gets it moving. You know, the engine room of pretty much any P5JS sketch is this thing called the draw function. You got to imagine this block of code is running on a relentless loop, like 60 times every single second. Each time through, it completely clears the screen and redraws everything. It's that constant refresh that creates the illusion of smooth animation. Now, what is so cool about this is how simple it is. To create the star of our show, this is literally it. One command, box 150. That one line tells 5p.js to draw a 3D cube, 150 pixels on each side, smack dab in the center of our world. But a static box is boring. To make it move, we need this line, translate. What this command does is shift the entire world's coordinate system before the box gets drawn. So by feeding a constantly changing number into that middle part, that yPos variable, we make the box look like it's floating up and down. So the real question is, where does that smooth yPos value come from? And this is such a classic, beautiful creative coding trick. See, the code uses a sine function, which naturally gives you this perfectly smooth, wave-like number that just goes back and forth between -1 and 1. The rhythm is perfect, but the range is way too small. And that's where the map function becomes a hero. It takes that tiny -1 to 1 range and stretches it proportionally to a whole new range, -800 to 800. The result is yPos, a variable that just glides gracefully between those 2 points, giving us that perfect floating motion. Okay, visuals, check. Now let's jump over to the other half of this equation and see how that incredible 3D sound is built piece by piece. You know, building audio with this API, it feels a lot like plugging together a modular synthesizer. First, you create an audio context. That's like your entire sound universe. Then you create a source, which in this case is an oscillator making a pure sine wave. Next, you pipe that signal through different effects nodes, like the panner node, which is what's going to position the sound in 3D space. And finally, you connect the whole chain to the destination, your speakers. And the absolute key to that whole audio chain, the star of the show for the sound, is created with this one line, the panner node. This is the piece of the puzzle that does all the heavy lifting and complex math for 3D audio. Really, the best way to think about the panner node is like having a tiny virtual sound engineer living inside your browser. Its only job is to take a sound you give it and place it at a very specific X, Y, and Z coordinate relative to you, the listener. It does all the calculations to make the audio feel like it's actually coming from that exact spot. So we've got a moving box and we've got a 3D sound engine. Now for the most important part, the code that actually builds the bridge between them and syncs them up perfectly. This line right here, this is the brain of the entire piece. This is the direct link between the motion you see and the pitch you hear. And hey, does that look familiar? It's our old friend the map function again, but this time it's being used as this brilliant translator. So what's it translating? Well, it takes the box's yPos variable, which we already know is smoothly moving between -800 and 800, and it maps that range to a musical frequency range, from a low 200 Hz to a high of 2000 Hz.
The logic is just so direct and beautiful. When the box is at its lowest point, the frequency is at its lowest. When the box is at its highest, the frequency is at its highest. It's a perfect one-to-one relationship.
But it's not just the pitch. The 3D position of the sound is also tied directly to the box. I mean, look at this. The exact same yPos variable that's being fed into the visual translate function is also being used to set the Y property of the panner node. The box and the sound source are literally physically locked together in space, both controlled by that one single elegant variable. Now, you can't just change an audio setting 60 times a second and expect it to sound good. If you did, you'd get all these nasty clicks and pops. So to get around that, the code uses this fantastic method, linear ramp to value at time. This basically tells the audio engine, hey, don't just snap to the new position. I want you to glide there smoothly over the next fraction of a second. It's basically the audio version of animation, and it's why the sound moves just as fluidly as the visuals. Okay, that core connection is just brilliant. But the things that really elevate this from a cool tech demo into a piece of art are the finishing touches. Let's dig into a couple lines of code that add some incredible polish. Remember how surprisingly real that 3D effect felt? Well, this one little setting is why. By changing the panning model to HRTF, the artist is telling the browser, don't use the simple, cheap 3D audio trick. Use the advanced, super realistic one. HRTF stands for Head-Related Transfer Function, which sounds complicated, but what it really does is simulate the way sound waves literally bounce off a person's head and into their ears. It accounts for those tiny differences in time and tone between what your left and right ear are hearing, which is exactly how our brains figure out where a sound is in 3D space. It's the absolute secret sauce for immersive audio, especially with headphones, and it's just built right into the browser for us to use. And the final artistic touch is all about adding sonic richness. See, instead of just one sound source, the code actually creates two. The main one is a clean sine wave, but layered very quietly underneath is a second triangle wave oscillator. Triangle waves just have a slightly different, softer texture. It's also set to half the frequency, a full octave lower, and a much lower volume. This subtle harmony adds this warmth and body that makes the sound feel so much fuller than a single sine wave ever could on its own. So when you boil this entire piece down, the technique at its heart is actually beautifully simple. It's all about mapping one stream of data, in this case the box's position, to control another stream of data, the sound's pitch and location. This single idea, this act of translating numbers from one world to another, is really the fundamental building block of so much generative art. And that leaves us with a really fascinating thought to end on. In this piece, position was mapped to pitch. But what else could we connect? What would a data visualization of stock market changes sound like? What would the rhythm of a person's breathing look like as an animation? The tools are right here, built into our browsers, just waiting for us to draw the next connection.